So welcome to the second video on the Ramachandranplot series. So as usual, what we are going to do is that we will recapitulate some of the things that we had learned previously before we go on to the details of today's lecture. So if you consider a peptide out here, now the conformation of the peptide in internal coordinates of course is made up of by the bond lengths, the bond angles, and the three different torsional angles, the phi, the psi, and the omega, around each amino acid. Now in general we can say that the bond lengths are nearly constant most of the time. The angles, they may change a little bit but are also close to being constant. And therefore the conformational changes, whenever the peptide changes its conformation, that happens due to changes in the torsional angles. And of course there are two torsional angles around each alpha carbon, namely phi and psi, and one torsional angle omega around every peptide bond. Now it turns out that the peptide torsional angle, thanks to a little bit of an electron delocalization between the oxygen out here and the nitrogen. So there's a little bit of an electron delocalization between the oxygen and the nitrogen, which gives this peptide bond a partial double bond character. And therefore, because of its partial double bond character, the peptide bond is held rigid, and it's generally in the trans conformation. So omega is around 180 degrees. Most of the time. So therefore the conformation of a peptide, we can say to a first approximation of course, is depends upon these two torsion angles, phi and psi, and there is of course one pair of phi and psi around every amino acid. So this phi this phi and the psi torsion angles around the amino acid, these we can take it that these are the major determinants of the peptide conformation. Now in his studies on peptide conformation, Ramachandran decided to work with a very simple model system which he called the alanine dipeptide. Essentially this is an alanine residue where the NH2 group, the amino group of alanine, was blocked with an acetyl group, and the carboxyl end of alanine was blocked again with an N-methyl amide. So this small molecule, again, it has the major torsional angles which can change the structure out here are these two peptide torsion angles, omega 1 and omega 2, which remain constant most of the time, and it is these two, the phi and the psi torsion angles around the C alpha carbon, which is here, this is the C alpha carbon. The phi and the psi torsion angles control the conformation of this alanine dipeptide. So having decided on his model system, Ramachandran then generated all possible conformations of the alanine dipeptide by varying the phi and the psi torsion angles, taking care that any conformation in which there exists a pair of non-bonded atoms whose distance falls below the cutoffs we had set, the normal limit and the extreme limit, then those would be considered disallowed. I repeat again. So if there exists any non-bonded atom pair, that is atom pairs which are not connected by a bond or even two bonds, okay, so these are not being considered. Other than that, if it takes any atom pair, okay, which as the conformation is changing, if these two atom pairs approach each other at a distance which is lesser than either the normal or the lesser than the extreme limit, and here are the normal and the extreme limits, then if any atom pair comes at a distance which is lesser than these distance, which means it comes in this region of the Hertzsprung energy map, then he considered them as disallowed. Okay? So having done that, he obtained this particular map. So where this is the phi and size are allowed to vary in their full range, minus 180 to plus 180, and he found that there is only a small region out here, okay, which turns out to be allowed in some ways. Now this particular region, which is called fully allowed, will have, there's not a single non-bonded atom pair. The distance between them is less than even the normal limits, so they are larger than the normal limits. Now in this particular case, this region, which you call the partially allowed region, what happens, there should exist at least one atom pair the distance between them is less than that of the normal limit, but is still more than the extreme limit, okay. And then finally all of these regions where there would be at least one atom pair whose distance is lesser than the even that of the extreme limit, so this was considered disallowed. And I had shown you an animation clearly explaining to you why conformations in this region of the Ramachandran map is disallowed. The reason being that the electron orbitals between these non-bonded atoms, they overlap, and that is not allowed because there will be very strong electron-electron repulsion. And if we look at the map very carefully, we find that there are different atoms, different non-bonded atoms. They come together, they come close to each other in different regions of the map, and thereby making the structures disallowed. Okay, so whatever we have learned out here, of course, this is specifically for this alanine dipeptide molecule, which is a very small molecule, right? While a peptide or a protein can be very big and with lots of different amino acids, so therefore lots of different phis and size. So while we have very strict allowed disallowed regions for the alanine dipeptide, what happens for a larger peptide? That is a very important question. Now one thing one should keep in mind, that even in a larger peptide, these allowed regions, they these allowed regions, they refer to the local conformation around the dipeptide. So therefore whatever is allowed for this dipeptide or whatever is disallowed for this dipeptide should be disallowed also for the larger peptide, right? So the local conformation of each of the amino acids will have to follow the Ramachandran plot, the allowed regions only. So whatever conformations the peptide can take up, and they must, each of the amino acids within the peptide must lie within the allowed region. Fine, we understand that. Now, but as a result of this constraint on the amino acid, the local conformation of the amino acid, what effect can it have on the overall peptide structure? That becomes another important question. Now here, the Ramachandran constraints are applicable on the local conformation of each amino acid, right? So fine. But once these constraints are applied, will they have any effect on the overall conformation of the peptide as a whole? So that's a very important question. Now, the answer to that is not something which one can say it very simply. So what we will do, we will start with some special cases, and before moving into the more general cases as found in peptides and proteins. So the special case we are going to consider is that of a polypeptide in which all the side chains, all the amino acids in the polypeptide are assumed to be identical. So that means we are talking about a homopolymer of amino acids, right? So all the amino acids are same. Now in such a peptide where all the amino acids are same, if it takes up an ordered structure, now if it is a random structure, then each of these amino acids can be in different conformations. But if it picks up an ordered structure, one can assume that the local conformation of all the amino acids should be exactly the same, right? After all, the conformation of a molecule depends upon its chemical nature. So since the local chemical nature as defined by the side chains, they are all the same. So therefore one can assume that the local conformation will also be the same. And the local conformation is defined assuming omega is absolutely equal to 180 degree and trans conformation fixed. So the local conformation is defined by this phi 1 psi 1 for the first amino acid, phi 2 psi 2 for the second amino acid, and so forth. So these torsional angles. And so if all the local conformations are same, what we will have? We will have all the phi angles, phi 1 are equal. That is, phi 1 equals phi 2 equals phi 3, and so on and so forth. Similarly, all the psi angles will also be equal. That is, psi 1 equals psi 2, psi 2 equals psi 3, and so on and so forth. Right? So the question is, what is the conformation of a polypeptide, a homopolypeptide, if you will, when all its phi angles are equal and all its psi angles are equal? Now, this question apparently seems very difficult. How can you talk about the structure of a large peptide, even though when all its phi sides are equal? Of course, I mean, I have not said that phi has to have this value or psi has to have that value. I have not said. All I am saying is that all the phi angles are equal to each other and all the psi angles are equal to each other. What kind of conformation does such a polypeptide make? To understand that, let's look at it this way. So here I have my polypeptide, and what I do is that I draw a little vector from the C alpha carbon atom of the first amino acid to the second amino acid, and then another vector from the second amino acid to the third amino acid, then another one third to the fourth, and so on and so forth. Right? Now imagine that in three-dimensional space, the first vector is going along this way. Now the second vector, of course, makes an angle with the first vector, and let's say that angle is theta. So let's call it theta 1. Now the second vector also makes an angle with the third vector, so let's call it theta 2. Now this angle, particularly out here, this theta 1 angle between the first vector and the second vector, will depend upon the conformation of this amino acid and this amino acid, right? So it will be dependent upon maybe phi 1, psi 1, phi 2, psi 2, that's all. Similarly, the orientation of the second vector will depend upon phi 2, psi 2, phi 3, psi 3, so on and so forth. But now, if phi 1 equals phi 2 and psi 1 equals psi 2, phi 2 equals phi 3 and psi 2 equals psi 3, so they are all same. So thereby, one can argue that theta 1 also equals theta 2. That is, it makes the same angle. And then the same argument follows. So from theta 2, I have theta 3, which equals this, and theta 4, which equals that. If that is the case, so it is like imagining, okay, let's say that I take a step in some direction. I take one step, and then I take a turn, a right turn, let's say, by 90 degrees, okay, and I take exactly one step and I come to another new place. Again I take a right turn and I come to a new place, okay, and I again take another right turn, and then I suddenly find myself that I am back to wherever I started. The same thing will happen here. So of course, how many steps it takes to come back to the original place will depend upon whether this angle is 90 or 60 or whatever. So if it is 60 degree, for example, then it might take 6 steps to cover. So because these 4 angles sum up to 360 degree. So if it is 60 degree, then I'll need 6 angles to make 360 degrees. So I'll need 6 steps. So it will be something like this. So of course, the number of steps may differ. But at some point of time, if I'm taking the exact same kind of steps, the same angle between the steps, then at some point of time I will cover and I'll come back exactly to where I started from. However, but since it is in 3-dimensional space, the thing is not so simple. It's that when from the first to the second, I'm of course taking a rotation by angle theta. I'm also doing some translation. I can also do a translation, right? I can move a little bit up or down. And if I do that, and if I keep on doing the same translations all the time, because even the translation will depend upon the phi and psi, so that also must be the same. Then while I will come back to the same place, but I will be shifted a little bit. And what it will look like is something like a spiral or a helical conformation, right? So when you come back to the same place, you complete the turn, but you are shifted up or down a little bit. Okay. So the basic argument which I am trying to make is that if I have a homopolypeptide in an ordered conformation, right, that is all the R1s are R1 equals R2 equals whatever, and all phi angles are same and all the psi angles are same, then the conformation of this peptide must be that of a helix. Okay. So this is a major statement, that whenever I have a homopolypeptide in an ordered conformation, in such a way that all the phi angles are same and all the psi angles are same, then that particular polypeptide must take up a helical conformation. Okay. So whatever type of helix it makes, but it will have to make a helix. So this is the argument. Now, okay, but it's all helices are not exactly alike, so it can form different kinds of helices, right? So we could look at what kind of helix it makes, but for that we have to characterize the helix. How many different kinds of helix are what are the parameters which describe a helix? That is something which you have to understand. So let us do that. So we can do that by considering a helix is something which is like a ribbon which is wrapped around a cylinder. That by definition becomes a helix. And of course these are, so here in yellow I have the peptide which is wrapping around, and in this dots out here I just refer to the maybe the C alpha atoms, that is one dot per residue. So having set up this system, we can now characterize the helical conformation in terms of the parameters of the cylinder. And how do we do that? So one of the things that we can do, as we move from one of the units of the monomeric units, maybe the residues, to the next residue, we make an angular displacement right from the center of the cylinder. And let's call that angle theta. Okay. So this displacement is equivalent in the previous example which I took. Yeah, is to that, if theta is equal to 90 degree, then it's like my step is a turn. But of course, it need not be 90, it can be whatever you want. So how many such monomers will cover a turn? Now, since the full turn is 360 degrees, so the number of such monomeric units, I mean like residues, which complete the turn will be 360 by theta, because each turn you make angular displacement of theta. The full turn means a 360 degree angular displacement, so which means the number of residues per turn is 360 by theta. That's fine. Now the second thing is that as we move along from one residue to the next, we also make a shift, a translation, which actually goes parallel to the axis of the helix, right? So we can have an axis of the helix. So we make a translation parallel to that, and that I will call H. Okay. Now the pitch of the helix, pitch of the helix, this is defined as the displacement along the helix axis as one full turn, right? So for each residue, the displacement is H, and there are n residues per turn, so the pitch will turn out to be n times H. And then the last parameter I have is R, or the radius of the helix, which is R. So these 5 parameters I can use to describe a helix. And as you can see, out of these 5, 2 of them are dependent upon others, right? So theta and n are related, and P again depends upon n and H. So essentially I can take any 3 of these parameters which are independent to describe a helix. So Ramachandran in his work mostly talked about n, H and R. So we will be using these 3 parameters to describe our helices. So now let's see. So to summarize this last bit is that we defined that our homopolypeptide, which has phi's and psi's are all equal, that must have the conformation of a helix, right? And and the helix we will characterize by 3 parameters, so which are n, H and R. Now, since the conformation of this molecule is governed by the phi and psi angles, right? So this n, H and R must be a function of the phi and psi angle. That is, they must be depending upon the phi and the psi torsion angles, right? In fact, given the phi psi torsion angles, just one phi and one psi is enough because all of them are equal. I can calculate the helical parameters n, H and R. So how does it look like when I do this calculation? And it looks like something like this. Okay, so here you can imagine now it's not just a dipeptide but becomes longer, but all the 5's and si's are same, making a helix which is characterized by these parameters N, H and R, and I plot them as a function of phi and psi. So this is the variation of N. Its N varies from 2 to about 6.5, right? And the colors indicate whatever in these regions, for example, is high as 6.5, while in the middle, this diagonal line out here is violet color. This is N is equal to 2. H, for example, varies between 0 to 4 angstrom. Now 0 is almost like a band out here, okay, while the edges of the plot H is very high, which is around 4 angstrom. And similarly you have the variation of R, which again also varies between 0 to 4 angstrom. Fine. So, but what do we make out of it? Now we actually, not very easy to interpret, but it becomes much easier to interpret if what we do, if we superimpose our standard Ramachandran maps onto this NH plots. Okay, so when we do that, here the white lines, which hopefully you can see, they define the Ramachandran map. Okay, and over the N plot, for the H plot and for the R plot. So the moment we do that, we can see that if we have homopolymeric structures, what kind of NH they will have. Now at the time of Ramachandran, there were some homopolymeric structures were known thanks to the work of Pauling, who discovered the structure of a fibrous protein, wool keratin, which has a very simple enough sequence, not exactly an homopolymer, but close by, and that had the alpha helical structure. And the silk fibroin, which had an extended sheet-like structure. Again, silk fibroin has a very simple sequence, not exactly a homopolymer, but something close to it. Ramachandran himself discovered the structure of collagen, which is again another repeating polypeptide, mostly glycine, proline. So again, not exactly a homopolymer, but close to. And also a few homopolymers were also, I think, polyserine, polylysine, etc. The structures were experimentally determined by them. And when they did that, and if you plot those phi and psi's, and they fall, at various ranges. So I can show you this. So for example, there's a pi helix, the alpha helix, 310 helix, and so on and so forth. Easier way to see it would be this plot where these helices are shown. So here you have pi helix, N is equal to 4.3, and H is 1.1, R is 2.1. Then you have the alpha helix, for example, which is well known. N is 3.6. You know that it is 3.6 residues per turn, and the shift along each residue is 1.6 angstrom. R is 1.6 angstrom, so on and so forth. And then you have the silk, the extended structure. N is equal to 2, H is equal to 3.5, R is very small, 0.3. So while pi is the thickest of the real fat helix, with R is about 2 angstrom, well, the silk fibroin is stretched absolutely thin, and well, R is only about 0.3 angstrom. What is interesting that some of these helices, for example, are the collagen and the so-called left-handed helix, they have a left-handed screw sense, while the others, they have a right-handed screw sense. Now what do I mean by that? I can see from here that if you see the pi helix in a ribbon form right now, when the ribbon is towards you, if we are moving from left to right, then it becomes a right-handed helix. If you see pi, alpha and 310, when the ribbon is towards you, you are moving from left to right. But in the left-handed helix, when the ribbon is towards you, you are moving from right to left. Okay, so this is the main difference. The collagen helix is also left-handed, but it's difficult to make out. The silk fibroin structure is completely stretched, and it's just like a stretched ribbon where the theta value is 180 degrees, N is equal to 2, and so it doesn't have any handedness. If you look at the NH map again, now this N is equal to 2 line goes cutting across the diagonal. So any structure which comes at the lower triangle, those will be right-handed, and those which are in the upper triangle, which includes the collagen strand and the left-handed helix, they will be left-handed. So we already see that this NH maps, N maps, H maps also we can calculate like that same way. And putting on the Ramachandran map, we can talk about already that what kind of structures these homopolymers will have. Or even some fibrous proteins whose sequences are very similar to homopolymers and they behave more or less the same way. Now comes the question, is that fine? I mean, homopolymers are a special case, where it is assumed that all the pi sides are same, so you will have a helical structure. Even these extended ones also, we can consider them to be very extended but helical in nature. But what about proteins, normal globular proteins, where of course we have some helices and some strands which you can model this way, but we have other things also. So how do you look at that? Okay, so let's take an example. So here is a very normal looking protein. I have quite a few helices, which are shown by the cylinders out here. Quite a few strands, which are shown by these yellow arrows. Okay, and then quite a few loops and coils and things like that. So what I can do that using a molecular modeling program, computationally of course, I can separate these helices and the strands and the coil and turn regions, and that's easy to do. Okay, computationally it's very easy to do. And then for each of these residues which are in the helices and strands and this, I can calculate the phi and size and I can plot them on the Ramachandran map. What I observe is that even though when you have the helical structures, normally the alpha helix, for example, I had said N is 3.6, H is 1.6 and all that, and in the Ramachandran map, the alpha helix comes somewhere here, minus 57 on phi, plus 57 on phi. But in the protein, what we observe is that for these alpha helices, it's not very, very constant. Okay, so it's not exactly minus 57 plus 57, but it varies in a certain range. But the range is not so much. Okay, it's a reasonably narrow range. Okay. Similarly, for the extended strands out here, when I plot them, the phi size are about both phi may be around minus 120 to minus 150 or even near to minus 180. Psi would be somewhere from plus 120 to going all the way up to plus 180. So again, a relatively narrow region of space is covered. So it's not spread entirely over the map. Okay. So this is something very interesting. So which means that even though these helices and strands, the phi size may vary a little bit, but they are roughly in a certain region. So whatever I have learned from the polypeptides, okay, the homopolypeptides, I can probably bring them out here with minor adjustments if need be. So now one thing is about the coil and the turn regions. Now they don't have, while the helices and strands, they have specific regions allotted to them. The coil and the turns can come anywhere. So I find some in the helical region, some in the extended strand region, some in the left-handed regions, and some, these are probably glycine residues which are clearly outside. Okay, now what does it mean? One thing it means that I can classify the Ramachandran map into a helical region where mostly the helices will lie, into an extended strand region where mostly the extended strands will lie. But I cannot do the reverse. That is, by looking at where the phi psi of a particular amino acid is coming, I cannot tell whether it will be a helix or a strand. If it comes here, I can say it is not probably going to be a strand, but it can be a coil or turn residue because they can come anywhere. So I cannot predict from the phi psi what is the local conformation, helix or strand or coil turn. I cannot say exactly, but I can do the reverse. I can plot in the Ramachandran map and say that, okay, this part of the region is helical and that part of the region is that of a strand. So I can say, for example, here, for example, that roughly this region, this is a helical region of the Ramachandran map, and anything which is above, mainly somewhere here, I can say these are the extended strand. And this turns out to be the left-handed helical region. Okay. So this we can do. So we can divide the Ramachandran map into regions, the helical regions and the extended strand region and the left-hand region by looking at protein structures. So whatever we have discussed for the simple alanine dipeptide, whatever we have discussed for homopolymers is with some adjustment still valid for normal peptides and proteins also. So this actually brings out the universality of the Ramachandran map. Okay, now one more issue that we have to tackle out here. You know, at the time when Ramachandran calculated his map, there were no crystal structures of large proteins. There were maybe 1 or 2 protein structures were solved. Maybe hemoglobin was solved already by then. Maybe lysozyme and a few others. I have to check up the history out here. But there were very few. And so while constructing the map, he built upon ideas which did not look at protein crystal structures. In fact, his normal limits and extreme limits, whatever he calculated, and as I said in the previous video lecture, that these distances were calculated by looking at crystal structures of small molecules, okay, simple amino acids, dipeptides, so on and so forth, not looking at large proteins. So one question comes in that if we look at nowadays, on the other hand, a large number of protein structures have been solved. So if we look at those structures, look at the amino acids in these protein structures, calculate their size and size, and if we plot them on the Ramachandran map, should we find any agreement there? If we find an agreement, it means that the Ramachandran, his ideas are applicable for large proteins also. And if there is no agreement, then of course something else extra is needed. So whatever Ramachandran said might be true for alanine dipeptide, but doesn't work for larger molecules. So anyway, so we can do that test, and we can plot here on the Ramachandran map conformations taken out from protein structures available in the databases. This particular map here, I have the steric Ramachandran map. The black lines show the Ramachandran contours, and actually what I also have is a lot of points out here. Each point taken from the represents one amino acid conformation taken from the database, and in the dark regions there are actually a huge number of points, and with the lighter yellowish regions there are lesser number of points. And I think the whole map contains more than 200,000 different residue points out here. So when we look at this this composite map, that is the steric map superimposed on the database distribution of 5' conformations of amino acids, what we see firstly is that there is by and large there is a good agreement. You see that majorly all the dark regions are within the allowed regions, and so majorly everything is within the allowed region, but there is a significant amount of amino acids, not very small. Mind you, this whole plot has about 200,000. So maybe 150,000 or more comes within here. But still, even if 5,000, 10,000 or 20,000 amino acids are on the outside, there is something to be said. Because from our previous knowledge, when we talked about, steric clashes and all this, we sort of said that not a single amino acid can exist in a conformation in the disallowed region, right? Because that would mean overlap between the electron clouds around the atoms. But how is it possible then that when we look at protein structures, we find a distinctly significant number of amino acids which are clearly in the disallowed regions? Okay, so there must be some reason for that. One reason is very easy to see, is that if you look at the amino acid, okay, now 19 amino acids out of the 20 which are found in proteins, they have a C beta atom. Alanine has only that, and while others will have more atoms on this side. Okay, now it turns out that if I have a C gamma, C delta and all that, they don't come very close to the backbone, so it doesn't really affect the backbone conformation so much. There is very slight effects here and there which are known, but we can ignore them for the time being. But the C beta atom, as we have seen out here already in this place, the C beta atom does make a lot of contacts and interactions with other atoms, so it is quite critical. Now there exists one amino acid which does not have a C beta atom, instead has a much smaller hydrogen, and that of course is our glycine. So what you see here is the so-called glycine dipeptide. If I take this glycine dipeptide and use this to calculate a Ramachandran map, it will miss all the interactions which are due to the C beta atom, isn't it? So will that map look like the standard Ramachandran map, or will it look different? In fact, when we plot that, it does indeed look quite different, and here is how it looks like. So immediately we see that a lot of extra allowed regions, particularly on the right side of the map, okay, they start appearing, okay, which was earlier not there. And I've plotted the glycine residues from the database into this map, and I see a fairly good agreement. Almost all the glycine residues are well inside the allowed regions of the map, okay. So one reason, while some of the amino acids which were apparently outside in this map may be due to glycines, right? So if I do something is that I take the same data, but now what I do, I'm sorry, not this one. Yeah. So I take the same data and I remove all the glycine residues, okay, from my data set. So this is all the amino acids, and this is the glycine residues removed. Now what I find? Now I find a fairly good agreement between the observed distribution and that of the allowed regions, but some points are still existing. Some clusters are there which are outside. There are 3 major clusters out here and something out here. I'll have a lot more to discuss about these in later videos. So keep this in mind that some of them are still outside. So what many people often do is that they calculate Ramachandran maps in a slightly different way. What they do is that they don't bother for all the steric arguments we made, clash, this, that, nothing. What they do, they simply take out the amino acids from the databases, okay, and then they plot them, and then they contour them depending upon the density of amino acids. So the dashed contour gives you a 90% probability that an amino acid conformation will be within it, and while the solid contour gives you a 99% probability that an amino acid contour will be within it. So if you compare these two, you find, okay, they are by and large, they look similar, excepting that, these extra regions are now incorporated in my database map, okay. So there are some differences. The question is, why these some differences? Because when we were making this map, we argued that anything outside is disallowed and this will involve a clash. But if we have something out here, what is it? Now, one of the reasons was glycine. So in this particular map, the glycine residues were removed. So glycine is not a problem. What are the other problems that might be there? Now, all of this will be the subject of next video, and maybe the ones after that. So we will be discussing all of this in detail. So as of now, I think I've spoken quite a lot for one video lecture. So maybe I will say goodbye here and wish you stay safe. Thank you.